Our goal is to start with a simple scalar field theory where we want to describe a collision of two particles with momenta k1 and k2 initially, and whatever happens when they collide at the end, we want them to have k3 and k4. So we are doing that for spin zero scalar particles with real scalar fields, and they obey the Lagrangian. The Klein-Gordon term describes a free field theory, and on top of it we have added an interaction term with a phi-4 Lagrangian. Lambda is the strength of the interaction, and the 4 factorial is just a convention. So our goal is to compute the amplitude of probability for this process starting from the many-path formulation of our quantum field theory. We have expanded the Klein-Gordon Lagrangian into its explicit form, and also we have the interaction term and the source term. So we already solved this path integral in the case where lambda was equal to 0. It turns out that with lambda not equal to 0, so when we have an interaction, we can't solve exactly, or we don't know how to solve exactly this path integral. So we need to do it with approximation, and in particular we will do it in perturbation theory, assuming that lambda is small enough so we can take a Taylor expansion of this path integral into different orders in lambda, and then truncate our expansion when lambda is small enough. But it will be a bit adventurous to start straight away with this path integral. So we will follow this book, and we will start with a simplified version of this integral, which Z called a baby problem, and then we will increase the complexity. In the baby problem, we replace the field, which is a function of space-time, by a single variable q. In this case, there is no integral over space-time anymore because we just have q. It's not a function of x, and therefore we don't have derivative either, and so we are just left with the mass term, the interaction term, and the source term. And the idea is to try to solve this integral using perturbation theory, so for small lambda. So we will take a Taylor expansion of this integral in terms of lambda. We would like to get rid of the q for n, because in that case that's a simple Gaussian integral we know how to solve. And in order to do that, we will rewrite this expression using derivatives with respect to j. We see that by acting for n derivatives with respect to ij on this quantity, we'll bring down exactly our factor q for n in the front. But because the derivative itself doesn't have any q, it can be taken out of the integral. Of course, now we end up with this integral, which we know how to solve because it's our usual Gaussian integral. And now we can recombine the sum over n in a single exponential term, where we got rid of the I because to the power 4 it is just 1. So we didn't really solve the initial integral because we don't get a number at the end. We only get an expression which involves exponential of derivatives times a function of j. Nevertheless, we don't have the integral over q anymore, and this is a useful expression when we are only interested in some orders of the Taylor expansion in terms of lambda and in j. So imagine that all we want is the first order in lambda and the fourth order in j. We want something which is proportional to lambda, therefore we only take the first order of the expansion of the first exponential. To get a term in j4, it is a priori tempting to take the second order of the second exponential because it's an exponential of j squared. However, this is forgetting the fact that we have already a derivative with respect to j. So if we only take the second order of the second exponential, we will have a j4, but this j4 will be killed by d4 on dj4. Therefore, what we need to take is the fourth order of this exponential in order for j4 to survive. The first derivative will bring down a factor 8, so we will have 8 times j7. Then the second derivative will bring down a factor 7 times j6, etc. So we see that we end up, as expected, with a term which is proportional to lambda and to J4. So of course, this is just an example. We can do other terms using the similar techniques, like for instance lambda squared J4 or lambda J0, etc. And if you do enough of those, you will recognize some pattern, and in fact which can be coded into what we call Feynman diagram. So the diagrams are made of vertices, that's a dot here, connecting lines. In this case we have 4 lines because we have Q4 in our integral, and the value of the vertex itself is proportional to lambda. In fact it is minus I lambda. We also associate a 1 over m squared to each of the line, and we associate a j to each of the endpoints. So for instance, the lambda J4 term can be written with different diagrams. We see that each of these diagrams has 4 endpoints, and therefore they will be proportional to J4. And they also have only one vertex, and therefore they are proportional to lambda. So now we can apply the rule in order to know how many 1 over m squared we will have. But in each case we have 4 lines. 1, 2, 3, 4, or here 1, 2, 3, 4, 1, 2, 3, 4. So we see that this diagrammatic rule gives us the correct dependence in M, as we got in the earlier example here. So it's quite powerful. However, it doesn't give us a prefactor, but sometimes we don't care about the prefactor. What we just need is the actual expression as function of M. And in particular, using the same rules, we can determine the dependence in M of other terms of the expansion, like lambda squared J4, lambda J0, etc.